Okay, so we're coming back to the series and parallel circuits now, and we're going to look at them in a little bit more detail. Now what I've got set up here, two cells, same as before, two bulbs in parallel, same as before, but now I've got three ammeters. Each ammeter will tell us the current at a particular point in the circuit, and it needs to be in series in the circuit whenever you're using an ammeter. And in a parallel circuit, what we would expect is for the electrical current to come out of the battery when I connect it, to go to the first bulb, and then to go to the second bulb, and then back. But in actual fact, what happens instead is that the electricity chooses one of the two routes, because this is a parallel circuit. So if we check the amount of current that comes out of the battery, or indeed returns to the battery, we've got 0.33 amps. But if we look at the electrical current that's going through this bulb, we've only got 0.16 amps. And if we look at the electrical current that goes through this bulb, we've only got 0.15 amps. Now there's a little bit missing. 0.133 should go to 0.16 and 0.17, but the wires will have a little bit of a resistance there. We may not be perfect, but we will find that the electrical current splits, and it either goes down this route to this bulb or down this route to this bulb, and then all the electrical current comes back to the battery. Remember, the current isn't used up, it's the voltage that's used up. If we go for the series case, things are a little bit different. Just put that to one side. We'll come back to the parallel circuit a little bit later on. Come back to the series circuit. We've got two batteries, two bulbs. We can see that the bulbs are dimmer, which should give us a clue as to what's going on. And this time, I'm only going to use one of the ammeters. I'll take the ammeter and I'm going to put it in the series circuit. It's very easy to add an ammeter to a circuit. You simply disconnect the wiring wherever it is that you want your ammeter to go, and you plug in your ammeter in its place and you get a reading. And I've got 0.14 amps current going to this bulb. If I look at the other bulb, I'll put my ammeter in here. Bulbs come back on again, and I've got 0.14 amps. And finally, if I disconnect my ammeter one last time, reconnect the circuit, then break it over here on the way back to the battery, and this time I've got minus 0.1413 amps. Now don't worry about that. If you're registering a negative current, it simply means that the electrons, the electricity, are flowing the other way. You can either choose to ignore that minus, or if you feel more comfortable, just swap the leads around, and you should find that the number doesn't change, but the negative sign will disappear. So in a series circuit, the current was the same all the way round. It didn't split. And the current was about the same between the series circuit and the parallel circuit. So they're receiving a similar amount of current. That doesn't explain why the series bulbs are dimmer than the parallel bulbs. So there's got to be something more to it. And the something more to it is the amount of energy or the voltage that's being carried by the electricity as it goes around the circuit. Now, to measure the voltage in the circuit, you use a voltmeter, and you might well use one that looks like this. It's got a V distinguishing it from an ammeter, but the biggest difference is that now we are measuring how much energy goes into a device and comes out of a device. So we're looking for the difference between the two, which is why voltage is often referred to as potential difference. Higher up the school you'll learn that when it's referred to potential difference, it's energy being taken out of the system, i.e. electrical energy changing into light or heat, sound, whereas if it's called electromotive force, it's the energy being put in. But they all have the same unit voltage, and for the purposes of these experiments we measure them in the same way, using a voltmeter. So if I want to measure how much voltage I'm putting into my circuit, how much energy I'm giving the electrons, well, I need to measure across my two batteries. And I find that I'm giving, again, negative sign simply means wiring's the wrong way around. Swap them over. I'm giving them about 2.4 volts. These two batteries must be a little bit old. Each one should give 1.5 volts, so we'd be expecting something closer to 3, but that's fine, it's enough to light the bulbs. But here's the thing, 2.5 volts goes into the circuit. This bulb only gets 1.25, only gets about half of the voltage. And this bulb again 1.3, half of the voltage. So the energy is being split. The electricity is going around the circuit, in the series circuit, and when it gets to this bulb it uses half of its energy to get through. When it gets to this bulb it uses the other half of its energy to get through. It doesn't need much energy to get around the wiring. So although the current is the same all the way around in a series circuit, the voltage is split between the components, and if I had 3 bulbs in there, then each one would be only getting a third of the total. If we go back to our series circuit, to our parallel circuit, first bulb, second bulb, and this is the thing, when you're building electrical circuits they can easily get a little bit messy, so probably best not to do what I'm trying to do, probably best to start your circuit again from scratch. But one bulb, second bulb, 2 batteries again, make sure that they are going in the same direction and that they are in series, back, and then reconnect your second and you have 2 bulbs. 2 bulbs, both bright, and we know that one of them is getting half of the current and the other is getting the other half of the current. But let's look at the voltage. Now I've changed batteries, so we'd better check to make sure that the voltage is similar to what it was before. And this time, in actual fact, we've only got 1.9 volts. These batteries even a bit older than the others. But 1.9 volts is plenty enough to make them bright. And the reason why becomes clear if I check the voltage across either of the 2 bulbs. So the first one, 1.8. The second one, 1.8. So we have all of the energy that the electrons that were that went this way were carrying going into this bulb, and all of the energy or potential difference or voltage that the electrons were carrying that went this way going to this bulb. And if I were to add a third bulb, then all of the electrons that went that route would give all of their energy to that third bulb, and 3 or 4 or 10 or 100 bulbs would all have the same brightness. They'd all have all the energy that the electrons were carrying from these 2 batteries. However, it does mean, as you increase the number of bulbs, that you are increasing the current in the circuit, which means you're using up the energy of the batteries a bit faster. More current flowing, each bit of current carrying that energy with it, so you will run the batteries down faster in a parallel circuit. But on the other hand, you can add more and more components, and as we said earlier, they can be turned on and off independently, and also if it's bulbs they stay as bright, if it's loudspeakers they stay as loud. So we're going to look at electrical circuits now. There's lots of things about electrical circuits that I could tell you, but I'm going to try and pick out just a few of the basics about series and parallel circuits and about current and voltage. So current, as we know, is the rate of flow of electrical charge. In a circuit it's normally electrons, and voltage is the energy carried per unit charge. Put them together and you have the power in the circuit, because you've got the energy per second. But let's consider what that means in terms of current and voltage in a series circuit. A series circuit, very straightforward. We have a cell, and then we can have as many as we want, but let's just have 2 bulbs in the circuit. So the current goes from the positive to the negative. It's what we call conventional current. We know the electrons will be trying to go to the positive really. The current will flow around the circuit. Now the current's only got one route. So in series, current is the same. It can't go off to the side, it can't get lost, so it's going to be the same. Whereas the energy that you're carrying, the voltage, is going to be shared. So if we have 3 volts here
Each one of these bulbs is going to get 1.5 volts. Don't ask me how they know, but the electrons know exactly what they're going to come across. If they know there's 2 bulbs, they share their energy 1.5 volts each. If they know that there are 3, they would split it 3 ways and each one would get 1 volt. Sticking with this, if we know that the resistance, how hard it is to travel, is 10 ohms, and we know that the current is equal to the energy that you've got, the voltage, divided by the resistance, then we will find that the current will be 1.5 volts divided by 10 ohms, which is 0.15 amps, current measured in amps. It also means that if we look at the circuit as a whole, we have 3 volts. In order to get our 0.15 amp current, then we must have 3 volts divided by both resistors, 10 and 10, because there's 2 of them, and that will give us 0.15 amps. And that means that the resistance has added together. You have to get past one resistance and then the other. So in a series circuit, the current is the same, the voltage is shared between the bulbs, and the resistance adds. Okay. Now in a parallel circuit, things are slightly different because we're giving the current different routes to take, and whichever route it takes, it's going to take all of its energy with it. So we sort of have the opposite effect. We have a circuit very similar to the one that we had before. I'll keep it as simple as I can do, but this is true for any circuit you can come across. We have 2 bulbs now in parallel and 2 different routes for the electricity to take. We have 3 volts, and our current can either go that way or it can go that way. Never goes both. Okay, so the current in parallel splits. In this particular case, because the 2 routes are the same, half the current will go one way and half the current will go the other way. The voltage is 3 volts to each bulb. And we can find the current if the resistance of the bulb, it remains 10 ohms. Then the current in either route will be 3 volts divided by 10 ohms, 0.3 amps. But in total, because we've got 2 different routes, it's going to be equal to 0.6 amps. Now, that means that because we've got the 2 different routes, we've made it easier for the electricity to travel. And instead of the resistances adding together, the total resistance is equal to 3 volts divided by 1.2 amps, which becomes divided by 0.6 amps, which becomes 5 ohms. In other words, by offering 2 different routes, each one carrying 10 ohms of resistance, we've actually halved the amount of resistance overall. We've made it twice as easy to travel, or half as hard to travel. So in series the current stays the same, the voltage is shared and the resistance adds together. In parallel the current splits, the voltage is the same for each route and the resistance is actually reduced